Hello once again. We are continuing with the improper integrals and we're going to talk about the comparison test. So sometimes we might need to find out if an integral converges or diverges. And the integral can be a bit complex, or it needs advanced calculations to determine the accurate results that would either give infinity or actually the exact number. So to simplify these tasks, we need what is known as comparison tests. Comparison tests actually allow us to find out if an integral converges or diverges. So let's suppose we have got a function, okay? Let's suppose we have got a function fx, and fx is greater than or equal to another function gx, and all these two functions, they are greater than 0 on interval ab. Then the following is true: if the integral of the function fx converges, which means if the larger integral converges, always the smaller integral of the same limits will have to converge. So to illustrate this, let's suppose we have a graph and then we have actually a function. Let's suppose this is fx. If we can actually come up with another small function less than fx, let's suppose this function is gx, okay? And gx, as you can see, is smaller than fx. So if the bigger function fx converge, that means that the smaller one will converge as well. Which means if an integral of the big function from a to infinity is equal to the exact number, or a real number actually, that means that gx, the smaller function, is always follows the bigger function in terms of convergence. Now, I hope that's very clear. Now, if the second point, if the smaller function diverges, which means if gx diverges, then so does the bigger one. I think here, this is very clear. This is actually, you have to understand this because it's very important. Here we are talking about if the smaller function diverges, automatically the bigger function will diverge. Meaning that here we have two scenarios. If the bigger function converges, which means the smaller one will converge as well. But if the bigger function diverge, actually it does not mean that the smaller one will diverge. No. The bigger function gives the information about convergence when it converges, which means if it converges, the small one will converge as well. The smaller function, if it diverges, the bigger one will diverge as well. So the smaller function will not give any information about the bigger function if it converges. So if it converges, it does not automatically mean that the bigger function converge. No. Okay? But if the smaller one diverge, which means it automatically means that the bigger one also diverge. I hope that's very clear. So these are the two scenarios that we have to understand. If the bigger function converge, then the small function also converge. And if the small function diverge, which means the bigger function diverge. Now, let us see how we can actually use the comparison test to find out if the function diverge or converge. Now, let's do examples. So we have the following example. So we have got an integral from 2 to infinity of the cosine x squared over x dx. So does this integral converge or diverge? What do you think? So let us see how can you use the comparison test. So here we have two options. We can either try to find the bigger function and see if that bigger function gonna diverge or converge. If it converge, then you are going to expect that the function will also converge. Or if the small function diverge, then we can actually say that the function is going to diverge. Now, let us see how can actually take out the smaller function from this function here. Okay, so taking out the smaller function, we're gonna use the fact that cosine, we know that the value of the cosine function lies between -1 and +1. So this means that cosine x is actually less than or equal to 1 and is actually greater than or equal to -1. Okay, because actually this function lies between -1 and 1, which means it has to be less than or equal to 1, because the maximum value of the x, of the cosine of x, is 1, and the minimum, the lowest the lowest value of the cosine x is -1. So here we can actually derive, or can come up with an equalities from this function. So if we square, so let us square the function. When we square x, cosine x is gonna be cosine x squared, or cosine squared, which means that we're gonna also square the other sides, the right side, which means it's gonna be 1. When we square the left side, we're gonna have 1, so it's 1 1. So at the end we're gonna have something like this. So we can just squeeze this, which means we can just have cosine x is less than or equal to 1, which means cosine x squared is less than or equal to 1. So that's why we only have this expression here. Now, this is a fact that the cosine squared is less than or equal to 1. So let's divide by x squared. So we're going to divide by this. So here we have just come up with the bigger function, because this one, cosine x, that means that the cosine x squared over x squared is less than or equal to 1 over x squared, which means this one is a small function. This one gonna be our gx, and this gonna be our fx, according to the definition that we have. And we say that if the bigger function converge, that means that the small function will diverge. So here, we know for sure that 1 over x squared will converge from 2 up to infinity will converge. Remember, this actually is because of the p. Actually is because of the p. Remember what we discussed at the general formula, that if we have got an integral from number a to infinity, 1 over x p to power p, if p is greater than 1, we say that the integral will converge. And if p is less than or equal to 1, we say that it diverges. So here we are sure that the function, the integral 1 over x squared diverge. So let us write that formally. So what does that mean? So it means, so if we take the integral okay, this one converges, okay, so it converges. So therefore we can say that, and the integral or cosine x squared converges. Yeah, as simple as that. As simple as that. Now, let us see another example. Now, here we have another example. Will this integral converge or diverge? So, we're about to find out. So, here, what you have to know, the important tip, the important strategy that you have to use when you're given, in most cases, when you're given actually the fractions, you have to know that when the denominator grows, it means that the number becomes smaller and smaller. For example, if we have got 1 over 2, when the number here, let me use a variable, let's suppose 1 over n. When the n grows, this number 1 over n becomes what? Becomes smaller. So that's a fact. That's what you have to know. And it's actually a fact, because the more it grows, it means that the number approaches 0. So here we can actually produce a bigger number, a bigger fraction, a bigger function from this function here, to find out if it converge. If it converge, that means that our function will converge as well. If it does not converge, then it will not give any information about the function. So we know for sure that 1 over x plus x is less than or equal to 1 over ex. Yeah, why? Because if we get rid of x here, if we remove x, the resulting fraction will be bigger than this one, because when we reduce the denominator, it means that our fraction grows. Okay? For example, 4 over 6 is less than, that's a fact, 4 over 5 altogether. And the 4 over 6 and the 4 over 6 is actually greater than 4 over 7. That means if the denominator grows, we are reducing the fraction. The fraction becomes smaller and smaller. And if the denominator becomes small, it means that we are actually we are increasing the fraction, which means we are making it grow. So in this case, if you remove x here, the resulting fraction will be greater than or equal to this function. So it's a fact that 1 over x plus e 1 over x plus e to power x is less than or equal to 1 over ex. Okay. This is one option. Let's see another option, because here, when you're doing comparison tests, you just have to be flexible and logical in your steps. Okay, when you're doing your steps, you have to make sure that they are making sense and they are logical. Okay, now people can use different methods to come out with a bigger function or smaller function. Okay, so but this strategy that I'm showing you, it works efficiently. But you can actually produce more. For example, here we know for sure we can also come up with another one, which means is less than 1 over x. Yeah, that's for sure. But we know that this one, okay, this one, though it's big, it's going to diverge. And when it diverges, it will tell us nothing about the integral, because we say that it has to be big for it to it has to be big, and it has to converge, so that we can actually conclude that the smaller function converge. And it has to be small if it diverges for us to conclude that the bigger function diverge. I hope that is clear. Now, that's why we are not going to use this one, because it won't tell us anything about the integral at hand. Now, let us find out 1 over ex. Does it converge or diverge? In this case, because we haven't studied, or there is no general rule about the exponential ones, so we have to find out by integrating. How do we integrate this function? Now, we can actually write it like this. And we can use u substitution. You can say u is equal to negative x, so that du will be equal to negative dx. Okay? Then replacing in the integral, we have the integral. So where there is, so we have got e, where there is negative x, they're gonna put u. But here we also have to come up with the limits. So we know for sure that the limits are 3 to infinity. Now, you remember in the last lectures, we saw how to integrate the limits, the integrals with infinity limits. So we said that we're gonna replace them with a t value. So actually this is gonna be coming from the beginning. This is gonna be limit, okay, limit as t approaches infinity of the integral 3 to t e minus x dx. Okay, you remember how we are doing it. So in this case also, we're going to have limit as t approaches infinity, but the limits, because we're using u substitution, which means we have to change the limits as well. So when, so the lower limit is gonna be actually, so we know that u is equal to negative x. So replace negative x by 3, which means u is gonna be negative 3. So we're gonna replace x by 3, which means u is equal to negative 3. So the lower limit will be negative 3. So replace x by t, which means u is going to be equal to negative t. That means that our upper limit is negative t. Okay. Then du is equal to negative dx. So we can actually, we have du is equal to negative dx. So divide by negative 1 on both sides, we have negative du is equal to dx. So we're going to replace dx by negative du. But this negative here is a constant. It can be put in front of an integral. So we're going to have negative du, okay, which has replaced dx. Now, let us integrate now. Now, integrating, we know that the integral or derivative of the function of the exponential is equal to the the exponential itself. So an integral of e to power u is the same as e to power u. An integral of e to power x is the same as e to power x. So we can use that fact to integrate the this expression. So we can put the negative sign can be put in the front of limit. So we have got negative limit as t approaches infinity. So integrating e to power u is the same as e to power u, and we're gonna have to integrate the limits from negative 3 to negative t. So this gives here we have the limit as e to power negative t minus e to power negative 3. So we're gonna actually take the limits. We're gonna put the limits. We're gonna actually integrate differently, separately. So we're gonna have negative as limit as t approaches infinity of an the function e to power negative t minus limit as t approaches infinity of e to power negative 3. Okay, make sure that you don't forget the sign. It's very important. So you have to be careful of the signs. So for sure, we know the exponential function looks like this. This is e to power x. Okay, as x approaches infinity, so when we go this way, as x approaches infinity, the function approaches infinity. The function approaches infinity. But if we have it the other way around, that is, the function e to power negative x actually looks like this. Okay, so this one, for this one, e to power x negative x, as x approaches infinity, which means when we approach infinity, positive infinity, as we can see, we approach 0. So here the limit here is gonna be 0 here minus, and here the limit of the constant is just a constant, which means e to power negative 3 is a constant, which means it's just minus e to power negative 3. Negative and negative is as a positive, which means the whole limit is going to be e to power 3. And this e to power 3 is the integral, is the integral of e to power negative x evaluated from 3 to infinity. Okay, so this means that this integral converges because we get a real number. This is a real number. Okay, and since it's a bigger integral and it converges, then we conclude that the whole the original integral have, by comparison test, then the original integral converge. So therefore, by comparison test, then the integral 3 to infinity 1 over x plus e to power x dx converges. As simple as that. Yeah, this is another example. Here we have this integral. Does it converge or diverge? Now, we can use the same strategy. We can try to extract a smaller or a bigger integral from the function that we have here. Now, here we know for sure that the sin function is between 1 and negative 1. So if we multiply by 5 on both sides, here we're going to have negative 5 is less than or equal to sin x, 5 sin x, and here you're going to have also 5. Okay, and then if we so in this case we shouldn't start with multiplying by 5 because it's gonna change. We are trying to make this expression to be in the middle. So let's start by raising power to power 4. Okay, so that we should avoid having a different expression. Okay, so we know for sure that sin x is between negative 1 and 1. So if we raise it to power 4, this is gonna be sin raised to power 4. Since 1 raised to power 4 is just 1, and negative 1 raised to power 4, because 4 is an even number, that means that this one becomes 1 as well. So since it's just 1, it can just be squeezed to that other side. So at the end we have this expression. Okay, then if we multiply by 5, so here multiply by 5, we have got 5 sin, which is equivalent to this one. And then here, if we multiply by 5, here's just going to be 5. Okay. If we add 1, here we also add 1. So here we're going to have 6. Okay. So if we divide by the root x, here also we divide by root x. So here we're going to have this expression 1 plus 5 sin to power 4 root x is equal to 6 over root x. Not equal, but greater than 6 over root x. And we have to find, this is bigger than this. Yeah, of course it's bigger, but if we integrate this function, remember that x, the p, for the p here, okay, remember this rule, we say that when p is greater than 1, then this one converge. And when p is less than or equal to 1, then this integral from a to infinity diverge. Okay? So that means that this integral, the bigger integral, is going to diverge. The bigger integral diverge. And when the bigger integral diverge, it does not tell us anything about the function. Okay? It could tell us anything about a function if it was smaller, according to the comparison test. So in this case, we can't definitely use this one to prove the comparison, to prove the convergence or divergence using comparison tests. We need to come up with another function, okay? Either we can come up with a smaller function. So how do we come up with this smaller function? Now, let us find out. We know that if we have got a function, let's suppose we have got x over p, okay? This one grows if x is large, okay? And p remains constant. Which means if we increase the value of x, our fraction is going to grow. That is a basic math. That is a fact, okay? And if x is a constant, so if x is a constant and the p grows, okay, then xp becomes small. So if we have a rational function, as the denominator grows and numerator remains constant, it means that the function decreases or becomes small and smaller. As the numerator grows and the denominator remains constant, it means that the function grows. To come up with a bigger function, for us to come up with the smaller function, we can reduce the numerator and keep constant the denominator. So here we can actually, if we take out the, which means we can write 1 plus 5 sin raised to power 4 over root x is actually greater than or equal to. So let us reduce the numerator so that we can actually come up with the smaller function. If you reduce the numerator, let's just take 1. I've already taken this one because it's gonna be difficult to integrate. So take the ones which are simple to integrate. Okay. Let me write it well. So let's just take 1. Because we have reduced the numerator, that means that we're going to come up with the smaller function. So actually this is fx, this is gx. Actually this is smaller than this one. So since it is smaller, and we know that, from 1 to infinity, according to P series, 1 over root x diverges. Okay, dx diverges. This according to P series, to P rule, not series. That's another topic. So then for sure that the bigger one, by comparison test, the integral diverges. Yeah, because this one is a smaller function, actually. And if the smaller function diverge, it means that the bigger one is going to diverge. But if it converge, then it tells us nothing about the convergence of the function. So that is for today. I hope that you enjoyed the lesson. So if you enjoyed the lesson, consider commenting, liking, and subscribing to my channel.